In this section, we will go over some very important theorems that discuss how many zeros you can expect with a polynomial function. With this, what we'll see is that all of these refer to the zeros of a polynomial as complex numbers. So just a quick review. A complex number is a number that can be written like this. A plus bi, right? Where basically a complex number has both a real and an imaginary part. The value of A is the coefficient of the real component, and the value of B is the coefficient of the imaginary part. Now, any number, all numbers are actually complex numbers. It's possible, for example, for the value of B to be equal to 0, right? So A plus 0i is a complex number where the imaginary portion is just equal to 0, right? So when you see this language that when it refers to the zeros as complex numbers, that also all numbers are complex numbers, right? But some of them, the coefficient of the imaginary part is equal to 0, right? So that language is used to kind of encompass all possibilities. So with that, let us just go over these theorems here. I'm going to erase this for the time being. The first theorem is the fundamental theorem of algebra. This theorem says that if f of x is a polynomial of degree greater than or equal to 1 with complex coefficients, then f of x has at least one complex zero. Okay, so this is saying that if your polynomial is at first degree or higher, it's going to have at least one zero, right? The linear factorization theorem. If we have a polynomial function, again, where the degree of the polynomial is greater than or equal to 1, and the leading coefficient is not equal to 0, then that polynomial function can be written as the product of the leading coefficient times a number of linear factors, x minus c sub 1, x minus c sub 2, x minus c sub n, where c sub 1, c sub 2, c sub n are complex numbers, right? So this is essentially stating that any polynomial function can be written in factored form. Now, and then the values of c sub 1, c sub 2, c sub n, and so forth are all zeros of the polynomial. My third theorem here is called the conjugate zeros theorem. And this theorem states that if f of x is a polynomial with real coefficients, and if a plus bi is a zero of the function, then its conjugate a minus bi is also a zero. So if we have a zero that has both a real and an imaginary part, right, where the coefficient of the imaginary part is not equal to 0, then its conjugate is also a 0. This is a fairly handy theorem because if we do have, if we're given the information that a certain complex number is a 0, then we automatically know a second 0 as well, right? Its conjugate. The number of zeros of a polynomial, if f of x is a polynomial of degree greater than or equal to 1 with complex coefficients, then f of x has exactly n complex zeros, provided that each zero is counted by its multiplicity. So this one is simply stating that the number of zeros of the polynomial will exactly equal the degree of the polynomial. A third degree polynomial will have 3 zeros. A fourth degree polynomial will have 4 zeros, and so on. Now, when it says counted by its multiplicity, this simply means that some of the zeros might repeat, right? You might have several zeros that are the same value, and that's what we mean by counted by its multiplicity. So what we will do now is we will work out an example, and where we will apply some of these theorems. And here's our example right here. Given that 1 minus 5i is a 0, of the function f of x equals x cubed minus 3x squared plus 28x minus 26, find the remaining zeros and factor the function as a product of linear factors. Okay, so first of all, this polynomial function is a third degree polynomial. And so according to the number of zeros theorem that we just looked at, that means this function will have exactly 3 zeros. Furthermore, one of the zeros is just flat out given to us. The zero 1 minus 5i is given to us, right? And because of the conjugate zeros theorem, we automatically know a second zero, which will be the conjugate of that. 1 plus 5i. Okay, so right off the bat, we know 2 of the 3 zeros. And there's only one that we need to identify. So to go through the process here of finding the third zero, I can start by doing synthetic division with the known zeros. And we'll start with 1 minus 5i. Come over here. 1 minus 5i. Set up my synthetic division. My coefficients here will be 1 for the x cubed term, negative 3 for the x squared term, 28 for the x term, and a negative 26 for the constant term here, okay? Now proceed, as we learned in class before, bring down the 1. 1 times 1 minus 5i is 1 minus 5i. Add to give me, if I add, I get negative 2 minus 5i. Okay. Now I have to take negative 2 minus 5i, and I have to multiply that by 1 minus 5i. Let's do that off to the side right up here. So I'm going to have 1 minus 5i times negative 2 minus 5i. And when I multiply here, 1 times negative 2 is negative 2. 1 times negative 5 is 1 times negative 5 is minus 5i. Negative 5i times negative 2 is plus 10i. Negative 5i times negative 5i is plus 25i squared. Okay. And then we want to simplify this down. First of all, the two middle terms can combine, right, to give me plus 5i. And then because I squared is equal to negative 1, 25i squared becomes negative 25. And all of this works out to be negative 27 plus 5i. And that is what I put right here. Negative 27 plus 5i. And then I add, and that gives me 1 minus 5i. And then once again, 1 minus 5i. Oopsies. Sorry, I made a mistake. That should be 1 plus 5i. Sorry about that. So now 1 plus 5i needs to get multiplied by 1 minus 5i. Once again, let's do that over here. 1 minus 5i times 1 plus 5i equals 1 times 1 is 1. 1 times 5i is 5i. Negative 5i times 1 is minus 5i. Let's see, negative 5i times plus 5i is minus 25i squared. Now, in this case, the plus 5i and the minus 5i cancel. I squared is negative 1, so negative 25i squared is just plus 25. That works out to be 26. Put a 26 right there, add to get 0. So it is indeed a 0. Okay. So now I'm going to do synthetic division again with the second 0. Now, because if 1 plus 5i we know is going to be a 0 of the original function, and that means it's also going to be a 0 of the quotient of the division that we just did. So when I do synthetic division a second time, I'll set it up over here. Okay, instead of putting the coefficients from the original function in there, I'll put the results of the first synthetic division down here. So I've got 1 minus 2 minus 5i, 1 plus 5i. Okay, so keep in mind that we started with a third-degree polynomial, right? And when you divide, the quotient is always 1 degree less, right? So this 1 right here will be the coefficient of an x squared term. This right here will be the coefficient of x term. This will be the constant. Okay, and this is just the remainder, which is 0. And when I do synthetic division again, I'm going to get a second quotient, which will be 1 degree less than this, right? So it'll be a first degree. So let's proceed. Bring down the 1. 1 times 1 plus 5i is 1 plus 5i. In this case, the imaginary parts just cancel out when you add, so I'm left with negative 1. Multiply to get negative 1 minus 5i, add to get 0. And this is the coefficient of an x term. That's the constant. That's the remainder. Okay. So now, after dividing twice, what's left is the quotient x minus 1, which is linear, right? So now two other factors can be, I know two other factors because I know two other zeros, right? So another factor will be x minus 1 minus 5i. And a third factor will be x minus 1 plus 5i. And apologies here, but this extra parentheses does not need to be there. There we go. Okay. So there is my polynomial written as the product of 3 linear factors. And then furthermore, I know the 3 zeros as well, right? So let's just, let's see, these are the this is the factored polynomial right here, okay? And then in addition to the 2 zeros that I identified here, the third 0 is x equals 1, because that's the value that makes this linear factor equal to 0, right? So these are the 3 zeros right here, okay? 3 zeros and then 3 linear factors. Okay, so I was able to completely factor the polynomial, and the only information I was given was that 1 minus 5i is a 0. Okay? Okay, let's look at another example. In this example, we are given some zeros, and we are asked to identify a polynomial that has these given conditions. So what we're told is we're asked to find a polynomial of lowest degree with zeros of 3i and 2. Okay? And then it says the number 2 has a multiplicity of 2, right? So, according to the conjugate zeros theorem, if 3i is a 0, then negative 3i is also a 0. And then the number 2 is a 0, but multiplicity of 2 means that it repeats twice, right? So what we have is we have a polynomial with 4 zeros. So the polynomial that we come up with will be a 4th degree polynomial because there are 4 zeros. That polynomial can be written as a series of linear factors. So this is according to the linear factorization theorem. We have a leading coefficient, and that is multiplied by a series of 4 factors. And each factor is x minus a 0. Okay? X minus 3i, x minus negative 3i, x minus 2, x minus 2. Okay? And a minus of a minus is a positive, so this is equal to a times x minus 3i times x plus 3i. Okay. Over here, let's go ahead and square this out. So we've got x times x is x squared minus 2x plus 4. Okay. And our goal is to multiply everything together and simplify the final result down as much as we can. I'm going to take x minus 3i and multiply that by x plus 3i. That gives me x squared plus 3ix minus 3ix minus 9i squared. Okay. And over here, the minus 2x and the minus 2x can combine, like so. Come down here. Obviously here the plus 3ix and the minus 3ix cancel, so I'm left with x squared minus, and then also I squared is equal to negative 1, so this becomes just x squared plus 9 times x squared minus 4x plus 4. Okay. And now I have to take x squared plus 9 and multiply that by x squared minus 4x plus 4. So x squared times x squared is x to the 4th. X squared times negative 4x is minus 4x cubed. X squared times 4 is plus 4x. 9 times x squared is plus 9x squared. 9 times negative 4x is minus 36x. And finally, 9 times 4 is plus 36. Okay. And then we see if there are any, let's see, x to the 4th, 4x cubed. Sorry, this should be a 4x squared right there. Okay. And then I can combine the like terms 4x squared and 9x squared to get a final result. X to the 4th minus 4x cubed plus 4x, oopsies, my apologies here. I got to combine those terms together. So when I combine 4x squared and 9x squared, I really get 13x squared. Okay, minus 36x plus 36. Okay. And that's my final result, again, where the value of a is the leading coefficient. And that can really be any number. Okay, we're not given enough information to determine what that value is. Okay. All right. We will do one more example. Okay. Find a polynomial p of x of degree 3 with zeros negative 2i and 4. And the polynomial must also satisfy the condition that p of 0 equals 32. Okay? So we got a third degree polynomial. That means this polynomial will have 3 zeros. We're given 2 of them, and we're told that minus 2i is a 0. And we're told that 4 is a 0. And according to the conjugate zeros theorem, if minus 2i is a 0, then plus 2i is also a 0. Okay? We'll start in pretty much the same way we did in the previous example. P of x is equal to some leading coefficient times a series of 3 linear factors, x minus negative 2i times x minus 2i times x minus 4. And this is equal to a times x plus 2i times x minus 2i times x minus 4. And let's go ahead and multiply the two complex factors with complex zeros together with imaginary components here. X squared minus 2ix plus 2ix minus 4i squared times x minus 4. And of course, these two terms cancel. I squared is equal to negative 1, so this becomes x squared plus 4 times x minus 4. And let's go ahead and multiply these out. X squared times x is x cubed. X squared times negative 4 is minus 4x squared. 4 times x is plus 4x. 4 times negative 4 is minus 16. Okay? And now we can utilize this information, p of 0 equals 32, right? So if I come down here and evaluate p of 0, if I come up here, when I replace x with 0, every x gets replaced with 0, right? So what that really means is that every term that involves an x is just going to disappear, right? So I'm left with a times negative 16 is equal to 32. And that allows me to identify what the value of a is, right? If I divide both sides by negative 16, I get a is equal to negative 2, which means p of x is equal to negative 2 times x cubed minus 4x squared plus 4x minus 16. And that is equal to, when I distribute the negative 2 x cubed plus 8x squared minus 8x plus 32 as my final answer right there. And that is it for section 2.4. Thank you for watching.